All right, chemists, in this crash course, we're going to talk about our very first unit together and just highlight a couple of things that might be useful for the AP, specifically matter, how we separate matter, and how we identify it. First of all, you should have no trouble distinguishing between physical changes and chemical changes when things change. Chemistry is all about matter changing, and physical changes are things like phase changes or anything where the identity stays the same is a physical change. Identity stays. A chemical change is when the identity changes in its simplest definition. And things to look out for are signs of a chemical change. Gas being given off, a color change, a temperature change. Things of that nature tell us likely a chemical reaction took place. After that, we talked a lot about separations, and you should know what some of these techniques do. Filtration, you've hopefully done a number of times by now. That separates solid, liquid mixture, specifically an insoluble solid, so I could get a precipitate away from an aqueous mixture of ions. Distillation is good for a liquid-liquid mixture. It's based on boiling something away because it has a lower boiling point, but usually useful when you have a mixture of liquids specifically. So maybe an organic liquid that happens to be water-soluble, and you want to separate it from water. The one that boils first will boil away. Probably the most difficult one to wrap our heads around is chromatography, because I suspect we have the least experience with that. And there's actually two types, paper and column chromatography. Most students have done some type of paper chromatography where you have literally a piece of paper that acts as your stationary phase. You submerge it in a mobile phase that's in some kind of a chamber. It could just be a beaker, and then maybe that chamber has hopefully a pool of liquid inside of it, whether it's water or what have you, and the liquid slowly rises up the paper by capillary action, just absorbing the liquid, defying gravity and heading up the paper. And if you have some sample of, let's say, a dye on that paper, it will slowly get pulled up by that solvent until it separates into its constituent, in this case, dyes, colors, and you could maybe separate a mixture of red, blue, and yellow out of what used to be, black in the beginning. We went into a lot of detail about polarity and how it relates to these things, but all you really need to know is that it's a way of separating a mixture into its components, and it's all about affinity for the stationary phase versus the mobile phase. That's what those things are called. We have a stationary phase, meaning the paper, versus a mobile phase, which is almost always a liquid. However, there are other types of chromatography out there. There's also what's called column chromatography. I suspect few of you have done this. The principle is the same. You're still talking about a stationary phase. Usually it's in a column, a packed column of some type of solid, like a silica gel or something like that, that actually fills the column up, and you elute it, which means you push a liquid through. So you push your mobile phase through the column, and you have some mixture of a substance that's along for the ride, and you can get it to elute out the bottom. It'll be what looks like a burette with a valve, and you get things to get dispensed out. And as the mobile phase pushes the sample through the column, it will separate, and the components will move at different rates, because some will stick to the mobile phase more, and some will stick to the stationary phase more. But the principle is the same. It's all about getting them to stick to things more or less than the other component. Paper chromatography is useful for just analyzing things, but if you actually want to separate large amounts, you would use column chromatography. So I'll say useful for larger amounts. That's called column chromatography. That's what that's all about. Okay, and then lastly in this unit, we looked at how to identify substances. We learned a lot of techniques. There's really only two that I think are worth highlighting because they're probably the most foreign from your own experiences in lab or whatever. IR spectroscopy tells us about the types of bonds. Bonds absorb IR energy and vibrate. However, mass spectrometry is a way of measuring molar mass. Measuring molar or atomic mass. And this was most useful because it shows isotopes. Individual isotopes show up separately as separate signals in a mass spectrometry readout. Okay, let's take a look at some practice questions. So first up, here is a mass spectrum of an element. And they want to know the atomic mass. Well, the atomic mass is a weighted average. It's a weighted average. Weighted average. So it's going to be between 185 and 187, so somewhere in here. But I can tell there's more of the heavier isotope, so it's not going to be exactly 186. It's going to be somewhere between 186 and 187. So if I go to the choices, A and B are out. The only ones that are between 86 and 87 are C and D. And D just doesn't make sense because D is so close to 187. I can tell that the ratio is a 40 to 60 ratio, roughly, of the two isotopes. It's going to be closer to 187, but not that close to 187. So C sounds like the best choice without a calculator. Okay, right below it, a jar labeled NaCl has a powder. The table below gives us some information. Which information is the most helpful in determining if this is pure NaCl? Well, anything could have a mass of 27.3 grams, whether it's pure or impure. Many substances have no color or look like a white solid, so D makes no sense at all. C is a good example of a physical property, but the fact that it has that density doesn't tell me that it is this substance or that it's got that purity. But the mass percent is definitely the best choice to this answer because sodium chloride would have a percent sodium equal to its mass of sodium divided by the mass of the compound times 100. That is a property based on constant composition. And it's a useful way to figure out the identity of a compound. In fact, if you fast forward to a crash course couple episodes later than this one, you'll see how we learn to take mass percentages and turn them into empirical formulas. All right, next on the multiple choice, why would IR spectroscopy be a good technique to confirm the transformation as I see below? Well, the main change that's happened, I can see that this bond has changed from a single bond to a double bond. Let me actually show you an animation of what happens when chemical bonds absorb light. This is courtesy of the University of Colorado. And I have a simulator that can shine photons of light. There's microwaves shining on an NO2 molecule. Microwaves cause rotation in molecules and molecular bonds. So it's actually also called rotational spectroscopy. If you kick it up to infrared, that has a higher energy of light, and you can see what the molecule does. It actually vibrates. In fact, vibrational spectroscopy is a key word to know for IR spectroscopy. Visible light is even higher in energy, and what happens most of the time with visible light is, if it's possible, the molecule absorbs it and gives off a color. And NO2 does happen to absorb visible light in that range, in the EM spectrum range, so it does have a color, and you can see that in the animation. If we went to ultraviolet light, this is enough to excite electrons or break chemical bonds. So when you get to UV, it's the highest energy and it actually breaks apart the bonds. So that's what those different forms of energy do. The key thing to look for IR spectroscopy is vibrations. That's what we're looking for. And I see those words in choice B. The absorption of IR radiation leads to an increase in molecular vibration associated with the stretching. That's the best answer. Pan down to choice D, it actually mentions molecular rotation. That's microwave spectroscopy. You're not going to be expected, I anticipate, to interpret a spectrum, but you might just need to know the differences in those terms. IR goes with vibrations, Microwaves go with rotations. Check out the other choices. The absorption of IR causes non-bonding electrons, meaning lone pairs, to transition to a higher energy level. Nope, that's not what IR does. IR causes vibrations. IR causes the electrons in the pi bond to transition to a higher energy level. No, again, we're not talking about excitation of electrons. Okay, the last multiple choice shows a paper chromatography to separate mixtures, and they're playing with the solvent mixture. They're seeing which one works best at separating the compounds. You just look at the picture and pick the one that looks like it has the best separating outcome, and that's got to be C, because I could imagine literally cutting these off of the piece of paper. Everything else has them virtually in contact with one another. Okay, last up, let's look at some free response. A pure element has the mass spectrum below. How many different isotopes are there? Well, there's 3 signals, and each one should be an isotope, so it's just 3. What's the average atomic mass? The weighted average is what it should really say, but that's what they are implying, and you have to know that. So I can tell it looks like we have about 10% of the 25. This looks just more than that, so I'm going to call this 11%, and that's good. This one looks to be just shy of 80. I'm going to call this 79%. You could probably just look at these isotopes and figure out what the element is already, but they want to see that you know how to do a calculation, so let's do that. So the average atomic mass as a weighted average is going to be the percentages, I'll just convert them to decimals, multiply the isotopes of each one. So 24 times 79% plus 25 times 10% plus 26 times the 11%. And when I plug that in, 24 times 0.79 plus 2.5 plus 26 times 0.11, I get 24.3 or 24.32. I don't think they would grade for sig figs here. And the atomic mass unit is the unit that we usually use for atomic masses and identify the element. You scope out a periodic table. This is magnesium. That's pretty darn close to what magnesium's atomic mass is on its table. Okay, so that's a quick rundown of the kinds of things that you might see on the AP related to matter and how we separate it and how we identify it. Thanks for watching.